So in our intro video, one of them that we watched, we actually taught or heard a little bit about forces. And it was on that second clip that we watched that we didn't watch the entire video. It talked about fundamental forces. And so when we talk about motion and we talk about how fast things move and how their velocity changes, we also want to talk about their force, because an object has to undergo some sort of force so it will move. All right? Do you remember Newton's laws from last chapter? And you talked about how that one of his laws, and we'll get to this at a later chapter, I just want to jog your memory. Do you remember how that you have to make an object move by actually putting a force on it? So that's the connection that we're making here. So it starts off by talking about that we have fundamental forces in nature that we can tag all other forces back to some way, shape, or form. And those four fundamental forces are gravity, the electromagnetic force, which is what magnetism actually comes from, how things attract positive and negative. Strong nuclear forces. Those are nuclear forces within an atom that hold the electrons together, the protons and neutrons together. And then nuclear force that holds the atom together. Sorry about that. That holds the atom together within itself. And everybody knows what gravity is. I just kind of skimmed over that one because I didn't think about going back and forth. So if these are fundamental forces, then what are we saying a force is? Well, in any of these four fundamental types of forces, every one of these is going to describe how an object can actually be affected by a force in order for it to move. So gravity, for instance, because that's the most common one, let's talk about how is gravity actually a force. Well, gravity is a force because it does not matter how far away from the surface of the earth that you get. If you stay within our atmosphere, gravity pulls you downward. And so does it pull you in a direction? Yes, it does, and that causes motion. So that's why that we're relating force to this motion chapter. So what are some of the properties of the fundamental forces? We're not going to spend a great deal of time on these because I'm not going to quiz you about what each one of these are, but we can just talk a little bit about each of them so that we can have an understanding, of what they are. The first one it talks about is going to be strong and weak nuclear forces. These are types of fundamental forces, but they only act over very, very short distances. For instance, how big is an atom? Not very big, right? And so those are only going to occur within the atom itself. What about the force of gravity? These are like gravity and then the electromagnetic force. Those are things that you feel every day. Gravity is what we call a long-range force because it can be felt over the greatest distance. I mean, you have to get over, I think it's 6,000 miles is the gap of our atmosphere. You have to get above that before gravity diminishes. And that's a pretty long distance, wouldn't you say? And then we have electromagnetic forces that are going to produce forces in things like magnetism, static electricity, and then even friction. And we're going to talk a little bit about friction today. Okay, turn the page with me. When we talk about these different types of fundamental forces, one of the things that we need to work together to understand is that they each have different strengths. And so it says here that the nuclear strong force is the strongest of all four of those, because those are the things that are going to hold your protons and your neutrons together in an atom. I, for one, am very proud that this is the strongest fundamental force, because I don't know about you, but I don't think we could all exist if our protons and neutrons just decided to just let loose, right? We are atoms put together. And so I'm pretty proud that that is the strongest type. The next strongest is your weak nuclear force. These are things that are 10 trillion times weaker than the strong nuclear force. So that's pretty big gap, but still, it's the second strongest of the 4 fundamental forces. Electromagnetic forces hold electrons near the nucleus, and that's why that we say that it is in relation to magnetism and things like that. It is about 1% the strength of a strong nuclear force. So it's the third strongest. And then, if you can even fathom, gravity is the weakest of the fundamental forces. It's still pretty strong because it's holding us down. But of the 4, it's the weakest. It acts over the longest distance. Okay? But compared to the 4, it's the weakest of any of them. So that just gets into context of how that any small object can actually have a force applied to it. Okay? So when we start talking today about examples of these things, you need to understand, doesn't matter how small an object is, it's still going to have force applied to it. So your main job today, remember we're finishing the chapter today? Your main job today is to understand, if I apply force to an object, what's it doing?
Gonna change.
It'll change in some way. So we want to be able to figure it out. So let's just talk about this. Some forces, you have to have contact between them in order to make that object's motion change, like Brandon said. So gravity, do I have to have 2 objects touching in order for gravity to affect it? No. I mean, gravity is most evidence when you're not touching anything. Exactly right. That's what I was going to say. If you were to jump off of an object, you feel gravity immediately, don't you? I don't necessarily pay much attention to gravity as I'm standing here, but gravity is the reason I'm standing here, right? If we didn't have any gravity, we would just be floating into space. So we have some things that we call our contact forces. And just like if you were to describe the word contact, these are when 2 objects are physically touching one another. When you push or pull an object, you are applying a contact force. So one of the most common contact forces that we can describe is friction. How would you describe the relationship between motion and friction?
Motion is like you going, and friction is like car tire hitting ground.
Okay, anytime that you have 2 things in contact, they are applying a force to each other. But do you feel like friction is helping the object move or hindering it from moving?
Hindering.
It opposes motion.
It is.
Okay? So it hinders the motion of the object. Eventually, friction can catch up to an object where that it stops its motion. So we want to make sure today that we figure out how that actually occurs. Field forces act over distances but do not require 2 objects to be in contact. Think about when you were little, if you played with magnets. If you had 2 magnets and you faced them to their opposing forces,
Push away.
they would push away from each other, and you could actually push one magnet around without even touching it, right? That was the cool thing about playing with them that way. So what about gravity? I don't have to be touching anything, like I said before, for gravity to affect us. And so those are what we call field forces. And so therefore they are not going to have to be in contact with anything. So let's gear our motion, our study back to the point of what happens if we have contact forces. These are the things that are going to be on your tests, okay? So is everybody on page 244? Everybody's going to be working with me here? Okay. forces can act to change the motion of objects. And we were just talking about that a second ago. If I want to know how force affects an object, I'm going to figure out what we call the net force on that object. So what is the net force? It is combination of all forces that are acting on that object at the same time. I want you to think about what is a net pay if you get a paycheck. That's what is left over after all of your contributions are taken out of that paycheck, right? So net forces are what's going to be the resulting forces of all the applied forces on an object. And there's a very, very simple way to figure those out. And so we will get to that idea. An object will accelerate in the direction of the net force. Whichever direction that your net force is greater, that's the where you're going to see the motion of that particular object. This idea right here is something that is so common that you don't even know that you've been doing physics this whole time. Like, how old are y'all? Like 14, 15? You've been doing this since you were old enough to actually do anything on your own and stand up on your own. And you're just now going to figure out that you've been doing physics this entire time. If you have a net force acting on an object, the object will accelerate. If there is no acceleration, that's because you have no net force acting on the object. So what do I tell, like if there's going to be a net force or not? So it gives you, let's look at this example first, and then we'll go back and define it. All right, so in physics, a lot of times we use arrows to describe motion, okay? And the size or length of the arrows describes the quantity. So if you see this top picture here, those two people are going to be pushing on that couch, and if you notice the shape and size of the arrows, they're the same. That equates to us as physicists at the moment that those two people are pushing with the same exact force. If there are two of the same amounts of forces on both sides, is one side greater than the other? This is what we call a balanced force. We can also put a value on it. Let's say that this lady is pushing with a 5 Newton force and the guy pushes with 5 Newtons. Are both the same?
Yeah.
Yeah. And just like we put a positive and a negative on velocity, we can also put a positive and a negative on these. The girl is pushing in what direction? To the right. She's pushing to the right, correct?
Correct.
So I could say that is a positive 5 Newtons. Which direction is the guy pushing? Left. We can call that a negative. So if you do a simple addition problem, that validates how that we said that was balanced, doesn't it? Positive 5 and a negative 5 makes 0. So that's what we call a balanced force. So what's it say about balanced? Balanced forces produce a net force of 0. What does that mean? An object experiencing balanced forces will not change its motion. Does it say it goes to rest? No. It says the object will not change its motion. In the example of the couch, it stays at rest because it was at rest to begin with. But if you have an object that has no change in its motion, it's because it's not experiencing any kind of overall added force. It stays balanced. This means that an object at rest will remain at rest. An object in motion will remain in motion if the forces are balanced. No change. It gives you an example here. There are many examples of balanced forces in daily life. A light hanging from the ceiling. It doesn't move up or down. It stays exactly where it is. Is its motion changing? Nope. So therefore, it's balanced. Let's look at an example down here of the second picture. How is this picture different than the one before?
They're both pushing on the same side.
They're both
All right, so we still have the same people applying a force. Agreed? So let's just pretend, I'm just throwing these numbers out there. Now you have two people that's pushing with a 5 Newton, and she's pushing with 5 Newtons. And they're both pushing to the left. So it's a negative 5 Newtons of force and a negative 5 Newtons of force. Are they balanced or not?
Nope.
No, they are not balanced. So, how is this different than the picture before?
The picture is worse balanced. So it gets one's a positive, one's a negative.
One's positive, one's negative.
And they're both going each direction.
Okay. And so, we didn't, in the first one, we said they're balanced not only mathematically, but it's because like one force wasn't greater than the other, right? It's kind of like a teeter-totter. But now, in the second picture, what do we expect that we're going to see if this were a real-life example?
It's gonna move over.
We'd see the couch moving. Because there's nothing over here on this right side or left side to block it, right? So when we imagine this happening, the couch is moving. We call this an unbalanced force. Listen, sir, I've already warned you about closing your eyes.
Well, just blink.
I don't care.
I swear I wasn't going to sleep.
Thank you. I'm going to make you swear on the physical science book.
Okay.
Yeah, 'cause that means a lot.
Yeah, right.
Now, when we look at this, how is the motion? We've identified the force, how the force is different. Now back it up with how is the motion going to be different? How's the motion different in this picture than it was in the first one?
Going one way.
It's going in one direction, right? So, the top one was a balanced. The second picture was the unbalanced. We said no motion on the top because it was originally at rest, right? What are we getting from an unbalanced force?
It's moving one direction.
Okay, it's moving.
Acceleration.
Would you agree that it may be changing its motion when we have an unbalanced force?
Yeah.
The couch was sitting still, But now
moves to
what?
the left.
now it's moving. So that's the most important vocab that we can say. When you have an object that has a net force that is greater than 0, the object will accelerate in a direction of that net force. So we're going to say that this object is accelerating to the left. Agreed? Well, your left. Okay? Let's see. Okay, I'm good with that page. All right, turn. So if we have objects that are moving because of an unbalanced force, most of the time they are in contact with something else. Okay? Like 99.9% of them. Because even when you have stuff falling through the air, that object is still touching air molecules. Okay? So when we talk about objects that are in contact with each other, we say that they have friction. Friction is the force that opposes motion between two objects that are in contact. Friction actually comes from electromagnetic forces because of the two surfaces that are touching. And so when we talk about this, it's because of the interactions between atoms that we get friction. So the rougher the surfaces, the greater the friction is between the two because of the types of atoms that they are comparing. I always use this example. Why do we have a greater friction on carpet if we were to roll a little Tonka truck on it compared to rolling the Tonka truck like on this floor that we've got in our classroom?
It was a carpet. Oh,
Wait,
it's
see,
a
the
rougher
carpet's
surface.
It's a rougher surface, right? When you think about friction, I want you to go crazy, just like detailed. Think about the carpet itself. Every fiber of the carpet, every one, touches the wheels of that Tonka truck. Every one of them. So not only do you think of just the surface of the carpet, but if you went to the microscopic level, it's like your toothbrush. Every one of those little bristles of that carpet that's sticking up touches the bottom of those wheels. So the car or truck is going along on the carpet. After so long, the fibers on those rolling wheels begins to just like the truck slows down because every one of those fibers touches the bottom. Okay? So in the process of doing that, it starts off fast, but the longer it rolls, what do you see? Don't act like you had never played with Tonka trucks.
It slows down.
Slows down. But how would we get more enjoyment out of these on this floor?
Because they keep on going.
Because even though this appears to be flat,
They can drift.
there's a little bit of texture on these floors. But is there as many fibers touching the wheels of that? No, nowhere near. So we get less friction on a slicker surface. Less friction equates to more motion to us. Would y'all agree with that statement? It gives you an example of friction is what allows us to strike a match. And we can always tell when friction is present because it produces heat. Two objects that come in contact are always going to produce heat because of their interaction touching. So when we're talking about types of friction, we can talk about, think about why does your engine of a vehicle, why does it put off so much heat? Number one, it's burning gas. Rotating parts. Do you feel like those rotating parts are in contact? Yeah. So why is it so important for me to go and have my oil changed or for Barry to change the oil in our vehicles? Why is that so important for moving steel parts?
Wait, you said
Friction. So the friction of the two steels
See,
don't
the
stop
more,
it from
if
moving.
you don't have no oil,
Yes.
alright, it's gonna see the rod,
Uh-huh.
the rod bearing,
Yes.
and it spins on that,
Yes.
and there's no oil in there.
Uh-huh.
It's gonna get real hot.
Real
quick.
hot.
And then it's gonna eventually seize up, and then
Uh-huh.
the crank's still gonna be turning, and then your rod's gonna break and go through your block.
So, and so let's talk about this. This goes back into the chemistry stuff that we just left behind. What's happening to, we just said that friction was making stuff hot because of the contact. What happens to that metal as it gets hotter and hotter and hotter?
It starts to melt.
It's because of the electrons, it turns color. But doesn't it become more fragile because the particles are moving so
The metal
fast?
becomes soft.
Then we get those things like he's talking about, they break. So, as it touches each other, the contact creates heat. They become more fragile at that state. But what helps us out in our vehicles and mechanical parts like that is using like any type of lubricant. And used to, you had oils that couldn't last as long because of the particles in them, right? They would get hot and they would wear out. They did not lubricate as well. But now you're starting to see a switch over to synthetic oils that last a lot longer, right? Used to, like when I was growing up, you had to make sure every 3,000 to 5,000 miles you started checking your oil about 3,000 miles because it would start to decrease, right, within your engine. Now, my truck that I have now can go almost 7,000 to 10,000 miles before you have to change that lubricant. The more contact you have, the more friction you have, right? And you're eventually going to see those objects that start to wear away based on that contact. Were you going to say something?
Yeah.
He said the same.
It does, yeah.
Every 6
But that's because it lasts longer. So what types of friction can we see? Kinetic friction is when you have friction between two objects that are moving. Have you ever heard the phrase kinetic energy?
Yes.
And that talks about objects that are in motion, right? So our little Tonka truck that we were talking about rolling on this linoleum floor, that's kinetic friction because it's moving. The truck is moving, but it's still in contact with the surface. So we have sliding kinetic friction and rolling kinetic friction just because two things are in contact. But there are other cases where friction is a whole lot greater in value. I guess if we go back to the mechanic example with your engine, that is also going to be a rolling and a sliding friction. Your pistons slide up and down in those cylinders. Rolling friction is where your gears are hooked together and they are moving. Okay? So what about static friction? This is a very high amount of friction. So high that it has completely opposed the motion of moving objects. You guys ever helped anybody move, like out of a house or something?
Yep.
And it takes a lot of energy to get something heavy like a freezer or a refrigerator or like a big couch. It takes a lot of force to get that started to move, right? And then when you finally get it picked up, you see the indentions in the floor. That is where that your static friction is so great. It is at its maximum amount that it completely stops the motion. What kind of forces do we see when you have static friction at its maximum?
Gravitation.
Gravity pulls it down and helps out. But do we see a change in the freezer's motion?
Yeah.
No. Not when it's sitting there.
It just sits there.
So if there's no change in my motion,
That means they are
even, which is a balanced force, right?
Yep.
Yes.
Alright, back to you were saying that metals when they get hot,
Uh-huh.
like fragile.
Yep.
How come when you take a regular kitchen knife
Yeah.
and you heat it up to 1,000 degrees
Uh-huh.
and you cut something like other metal, why does it design to break? Like the other metal.
Well, when we talk about different textures like that or different compositions like that, different metals have different behaviors. And so a lot of it has to do with what that particular thing is going to be made from. So like things in your engine, because they're going to withstand such high heat and frequent motion, you're going to use something, or the company is going to put together those engine parts with a type of metal or a combination of metals that can withstand a whole lot of heat and a whole lot of motion. Whereas like jewelry and stuff like that, it's going to be made with metals that, aren't as durable.
So is that why like made out of stuff that can melt so they can bond together?
Uh-huh. Yep. Yes. Uh-huh. The last thing that it talks to you about, and we've already kind of talked about this, friction is something that we actually use every day on an everyday basis. And so in the process of looking at friction, it is something as simple as us walking across the floor is an occurrence of friction. If I didn't have something pushing back up like on the toes of my shoes when I walked, I'd fall flat on my face, and so would you. Okay? We can also talk about friction in terms of how the two objects are occurring together. Like, for instance, why am I not falling through the floor right now, or you, because gravity's pulling us down? Well, we have an opposing force that's holding us up, right? So when we start talking about forces in everyday motion, we're talking about that a lot of things, whether it's friction or just an overall force, you're going to have some balance. We are not falling through the floor, so we can almost say and venture into the thought process that the floor is pushing up on us with just as much force as gravity is pulling down on
So
us.
they're like equaling out.
They're equaling out. Okay? So as we go through and we look at all of these things, and then here is where we kind of jumped the gun and talked a little bit about that. Sometimes we do certain things to decrease friction. I don't know about you, but like if I get a new pair of boots, I slip around on those things until I can get the bottoms of them scuffed up some. Right? Have you ever had a pair of new shoes and the bottoms were slick?
Mm-hmm.
Well, that's an everyday use of friction. How do you keep from, like falling down? Well, you've got to do something to rough up the bottom of those shoes, and therefore you have increased the friction of that surface. Right? Why do you not walk across a wet floor?
Cause it's slippery.
It's slippery. The wet water on top of that has decreased the amount of friction, right? And we can't stand up as well. So you incur friction on an everyday basis. And it's one of those things that's so common that we don't really recognize it anymore.